So this is part 4 of how faster than light is ignored. So I'm picking up from part 3 and now dealing with how things are messed up when bringing the relativity point of view into the domain of quantum physics. I'm using the letters FTL to mean faster than light speed c in vacuum free of influences of field. The process that modern physics seem to be engaged in is make a mess, then keep adding more mess on top of the initial mess and never stop. So it takes a great deal of effort to try to deal with explaining that. Dealing with the work now of the following people. So I'm dealing with a video which I'm going to show about proving the universe is not locally real. The start of the video is as follows.
Quite literally some of the smartest people who have ever lived being confused, and how ultimately Einstein was proven wrong, which doesn't really happen all that often.
So that video clip says some smartest people who ever live being confused, and I say they're confused because they want to believe in Einstein, but they have to move goalposts for Einstein to mean something else than what they thought he meant. So the sense in ultimately was proven wrong is they thought Einstein meant such and such, and then had to revise, which is move the goalpost to have him mean something else, i.e. to change Einstein's relativity. So if you're trying to show Einstein's relativity wrong, you're faced with it being defended by people who change it.
That idea of locally real is made up of two concepts. Locality is the idea that things are only affected by their local environment.
So he's going to point out the concepts which is based upon. The first concept is locality, and that's really special relativity's light speed postulate to a large extent, and that's going to be modified by them.
You can't flick a switch in another galaxy hundreds of light years away and instantly see the results here, because nothing, not even information, can travel faster than light.
So he's explained locality, and the idea is going to get modified though from nothing travels faster than light, meaning the light speed c. And next he's going to deal with realness. One of the issues I have, I don't really think Einstein's relativity, special relativity, should be interpreted as having the speed c as a limiting speed, but that's the interpretation they're putting on it at the moment, and which it will then later modify.
Realness, though, is much harder to explain, and that is the focus of the Nobel Prize.
So he's pointing out the focus of the Nobel Prize for these people, and skipping over a bit of music where nothing is said. He next points out that in the 1930s there were two main paradigms in physics, and those two were Einstein's relativity and quantum physics.
Let's start close to the beginning, around the 1930s, where there were two paradigms, two ways of thinking about the physics of small things.
So those two ways means Einstein's relativity and quantum physics, but I can just focus on special relativity part of Einstein's relativity and put aside the issue of general relativity and just consider special relativity versus quantum mechanics.
Like particles, atoms, electrons, photons, etc. The view of Einstein.
And of course, particles is what physics is dealing with.
Einstein and many others was that the universe is real, that particles, atoms and electrons have definite properties that are inherent to them regardless of if they are being measured. Essentially, that if a tree falls in the forest and no one is around to hear it, it does in fact make a noise.
So the viewpoint of Einstein is realness. Reality exists if not observed. Those going against that idea is a group building on the idea of uncertainty. And that's Heisenberg's uncertainty, and that's coming from quantum physics.
And then there was a countergroup, the anti-realists, championed by people like Bohr as well as many others, that particles have properties that haven't really made up their minds until you actually go out and measure them, that they exist in a wave function of possible states, and only when you actually take a measurement do they really make up their minds. The famous example here is that of Schrödinger's cat that is both alive and dead until you look in the box, and then ultimately you go to prison.
So the group, which let's just call them the anti-realists, are opposed to Einstein's view on realness. And the person in the video made a comment, go to prison. I think he was trying to make a joke there, but it just went flat. Anyway, Schrödinger's cat is about wondering if a cat in a box is dead or alive, and there's a 50-50 chance of either, and you can't tell until you look. And that is suggestive of can't tell about reality until look at it.
This back and forth between Bohr and Einstein culminated in a famous paper called the EPR paper, where Einstein, Podolsky and Rosen put forward a thought experiment that they thought perfectly highlighted that quantum mechanics at best was incomplete and at worst may be totally wrong. Their thought experiment focused on an idea in quantum mechanics called entanglement, that the property of two particles can be inherently related. Their line of reasoning for their thought experiment started with, well, we know that energy is conserved. Things don't suddenly start moving in a direction unless someone or something pushes or pulls them. Neither also do they suddenly start spinning, rotating, jumping up and down, or doing anything else unless someone else is directly affecting them. Number two, if we start with a small quantum mechanical particle that isn't spinning, moving, or doing anything else, let's imagine that particle spontaneously breaks into two. If we look at one of those pieces it breaks into and find that it's moving to the right, we know instantly that the other particle must be moving to the left to conserve momentum. Or if we had looked at it and found that it was spinning one way, maybe clockwise, we would know instantly that the other particle must be spinning counterclockwise to conserve angular momentum. You'd be confused if you looked at this system and saw both particles suddenly moving to the right. Your intuition would tell you that some outside force maybe must have hit them. Or for the same reason, though maybe less intuitively, because most people don't think about angular momentum or spin, you'd be equally surprised if you saw both particles rotating in the same direction. You'd assume that something must have hit them and caused them both to start spinning. Step 3. Quantum mechanics here says these states are impossible to know before you go out and measure them.
So Einstein argued a lot with Niels Bohr about physics, mainly quantum physics, and he based on that argument eventually led to the EPR paper, and that led to the idea of entanglement. And this is sort of like the background we need to get to the issue of FTL, faster than light speed c in vacuum. And what comes next is the following.
If you separated these particles light years apart and measured one, say, and found that it was spinning clockwise, you'd know instantly, even if that particle was a universe away, that its counterpart must be spinning counterclockwise.
And that's FTL, faster than light speed c, where we're talking about light in a vacuum, free of the influences of fields such as the field of gravity.
But how could this be? If they really only take on a definite value when you measure them, and the other one always needs to be the opposite of what you've measured, then the particle that you did measure would need to instantaneously communicate to its partner and tell it to adopt the opposite value permanently.
Instantaneously, that means FTL, faster than light speed c, and he's going to query that next.
Einstein argued that this was impossible because it would have violated locality and meant that information had travelled instantly, faster than the speed of light, to tell the other particle to collapse its wave function and make up its mind which way it was.
And so Einstein argued against this FTL, faster than light speed c, and it violated what he thought to have meant by light speed constancy as a speed limit. And I think he was misunderstanding special relativity by the point in time when he was thinking that. It's a conflict of what they want to assume about non-reality with Einstein's light speed postulate assumption. Non-reality violates locality.
Instead, he argued, it must have made up its mind at the very beginning, when it was created. We just didn't know it, or we weren't smart enough yet to find a good way of measuring it. He called this unknown knowledge hidden variables, and said that this was the piece in quantum mechanics that was yet to be completed.
And he turned out to be wrong, namely Einstein turned out to be wrong, and there's not local hidden variables. If you still want hidden variables, then they need to be non-local, i.e. violates light speed c limit, and that leads to two groups of people believing different things.
And for around 30 years, physicists really kind of split into two groups. Either they sided with Einstein or they sided with Bohr. Mostly because no one had really come up with a good theoretical or experimental counter-argument to Einstein's EPR paper.
So skipping over some music to get to the next bit.
That was until about 1964, when John Bell, an Irish physicist on sabbatical from working at CERN, started to do some more theoretical work of his own. These works, which were later called Bell's theorem or Bell's inequalities, of which there are many different forms, but the underlying idea is to try and get the universe to pick a side, tell us whether there's hidden variables and Einstein's right, or tell us whether truly there is a wave function and that quantum mechanics is real. Now,
So really it is a local hidden variable idea of Einstein and a few other people versus the quantum physics ideas of Bohr and his quantum physicists such as Heisenberg.
Now this hinges a lot on what happens to quantum objects when you actually go out and measure them. So let me introduce you to the idea for a particle of light called a photon. Photons have a property called polarization, which describes which way the wave of light is oscillating through space, either vertically or horizontally, or potentially somewhere in between. If you wanted to measure which state a photon was in, you would put it through a polarizer that lets through either vertical light in one orientation, or it will only let through horizontal light in another orientation. But then at least your detector, which you place behind that polarizer, knows what sort of light it's detecting. If you fired in randomly polarized light, some of it vertical, some of it horizontal, some of it in between, by placing a vertical polarizer first, then a horizontal polarizer after, you would expect correctly to see that no light reached your detector because all polarization angles had been blocked. You can see this effect when using polarizing films, which are the same stuff you find on a pair of polarizing sunglasses. By orienting two polarizing films at 90 degrees to each other, you see no light emerges through them. What is interesting here is that if you place a third polarizer between these two, you suddenly, and I think quite counterintuitively, start to see more light. This is because fundamentally, measuring a particle changes its state, allowing light to slip through the final polarizer where usually it wouldn't be able to. So you start to see more light than you would otherwise expect.
Light affected by measurement, i.e. is then affected by observation, is an interesting comment. And he's now going to jump back, as he now says.
So let's jump back though into the story. At this point in history, Bell's work was still more theory and thought experiment than anything else. And that classically is the problem with theoreticians. If you look at them from a distance, it just looks like a wizard trying to have an argument with you.
So his comment, wizard trying to have an argument, and the Monty Python clip, which is a comedy group, is all just trying to make a joke over something complicated, i.e. bluff off something that doesn't make sense.
Physicists really needed to find a way of actually completing an experimental measurement. One of the early and most elegant and now heavily evidenced extensions of Bell's theorem work is the CH-SH inequality by John Clauser, the Nobel Prize winner that we're talking about here, Michael Horn, Abner Shimony, and Richard Holt. And their work here makes this theorem that Bell developed actually experimentally testable. The scenario they describe is similar to what we talked about before.
What's he going to talk about now is similar to what you've been earlier talking about, so I'm going to skip over it. And if you're interested, see his video. So I'm getting to the bit now to where he says it's confirmed by experiment.
The other. And in 1972, it was John Clauser who built the first experimental setup capable of conducting this measurement. In the paper that he released that year, this was the figure that he displayed, exactly matching the prediction of quantum mechanics, proving that the universe isn't locally real, that Einstein's deterministic view was incorrect.
So next comes a story which don't know if it's correct or not.
And the story from this point goes, I'm not sure if it really happened or not, that excited by proving the result, Clauser runs into Richard Feynman's office to tell him the news, and in classic Feynman fashion, Feynman throws him out of his office for ever doubting quantum mechanics and tells him, "Good, now get on with some real physics."
So that story is just padding to try to make things sound human in what would be just physics that was boring to most people. So it's a humorous little story just to divert your attention for a moment.
The other Nobel Prize recipients, Elaine Aspect and Anton Zeilinger, closed important loopholes that remained within this experiment, as well as showing that quantum entanglement can be transferred to other particles in a process called quantum teleportation. All this to say that without a doubt, the universe showed itself to be stranger than even Einstein had imagined.
So his comment, stranger than even Einstein imagined, and that's, in other words, Einstein incorrect. But now, instead of going back to Newtonian physics, they modify what they think about special relativity.
All of these phenomena are really the backbone of what is driving the modern quantum computing revolution. The idea that at some point in the hopefully near future, quantum computers will outperform classical computers because they have this inherent baked-in advantage that down at their core, their particles that run them are communicating to each other.
So this issue of applying quantum mechanics to computing, I'm going to pass on because I'm complaining about the relativity part.
This doesn't prove, and I can absolutely forgive anyone for on first hearing thinking it, that people can now communicate faster than light, or that it would be possible to derive some faster than light communication. That, unfortunately, is where the field pretty unanimously says no.
What doing now is wanting to say no to proper faster than light FTL, is wanting to impose light speed c as a limit still by using this issue of randomness.
This is ultimately because the core to this phenomenon is inherent randomness.
So when he says core to this phenomenon is randomness, he's going to use that as an excuse to keep imposing c as a speed limit.
At the source of that photon or entangled particle generation, and then also at those measurement points. Each photon will either make it or not make it through a polarizer. Each photon will either be created in some combination of states, but ultimately those combination of states will be impossible to know until measured. There's no way of loading information onto that communication channel.
Means that he thinks there's no way of imposing useful information onto that randomness. There are people who have claimed to have sent useful information, but I suppose he's just ignoring that or doubting what those people claim.
Channel. And as a result, there is no way of violating Einstein's fundamental contribution, which is that the speed of light is a fundamental limit in the universe. That absolutely stands correct, and I think would keep Einstein reasonably happy.
So, has concluded Einstein correct, despite pointing out earlier Einstein wrong. So you can twist things around. Einstein wrong, but if you modify him, then he becomes correct again, and that's what they think. So what really is happening is a revising of what they think Einstein means. Thus what we have is a reinterpreting of what Einstein said. There is nothing in Einstein's 1905 paper on special relativity about useful information versus random information. So how they want to interpret special relativity suddenly becomes random is information not limited by C, useful information limited by C. And that is on the quantum physics scale of things. But as per previous video, when dealt with galaxies on general relativity, there is no such restriction. So they are trying to make an artificial restriction which isn't there. On top of this, they have come up with the concept of local light speed, combining what they call locality, where you get the word local, that gets added to light speed to give local light speed, a concept that is ambiguous in the literature. Thus the method becomes they mistranslate and misunderstand Einstein's relativity and still resist correcting that mistake, which would return them to Newtonian physics with its speeds unrestricted by C. And I've dealt with these sort of things in previous videos. So the summary becomes the basic idea: the mistake is made by having special relativity falsely imposing a speed restriction of C given force physics paradigm, and in the case of quantum physics, when having a need for speeds greater than C, then they move the goalpost and pretend random information can go FTL, faster than light speed C, but not useful information. That's it, that's the end. So that's the end, thank you.